All right, let's say something about L'Hopital's rule. So we're talking here about limits of ratios of functions. Here we have f of x and g of x. So if we take their ratio, we get another function. And we've seen some of these examples before. Of course, x squared over x is x. And when x goes to 0, that goes to 0. Sine x over x, we know that goes to 1 when x goes to 0. This one we haven't looked at yet. It's kind of an interesting case. We'll talk about that more later. All right. So these all become 0 over 0 at x equals 0. So this expression 0 over 0 is meaningless. You need to investigate more about the functions on top and on the bottom to find out what it is. Okay. Now, and let me cut directly to his first idea about L'Hopital's rule. You probably have seen this before. If you take the limit of f of x over g of x as x goes to a, that's the same as the limit of f prime of x over g of x, g prime of x as x goes to a. Normally this limit is f prime of a over g prime of a. Now it's possible that f over g is a 0 over 0 limit, and f prime over g prime is also a 0 over 0 limit. A simple example of that would be x squared over x squared. Of course that's just 1, but let's leave that aside for a moment. If I take x squared over x squared, I would get f of x equals x squared, g of x equals x squared, right? And then of course x squared over x squared, as x goes to 0, then of course that's a 0 over 0 limit. But if I take f prime of x over g prime of x, well, that's 2x over 2x. It's still 0 over 0. All right, but if I go to f prime and g prime, of course I get 2 over 2, which gives me 1. Okay, so the general form of L'Hopital's rule says that I can take this ratio of derivatives and keep differentiating as many times as I want, and until I get a non-0 over 0 limit, and that's the same as my original limit. Okay, you can apply L'Hopital's rule repeatedly. All right, now the usual way of understanding L'Hopital's rule. All right, before I get there, let's do some caveats here. What he's saying is that here's a case where f and g both have a 0 limit at a. Okay, and the idea is that the size of f near a compared to the size of g near a is determined by their derivatives, right? F and g are both 0 here, but if I'm out here, say for instance, this value is about 3 times as big as this value. Why? Because the value here. Let me draw the picture. Okay, I'll grab it and draw the picture. That's his point here. Okay, all right, go over there. All right, we'll move it over here. All right, and make it bigger. Here we go. All right. Suppose I look out here at this point here. All right. All right. And I'll take the function here and the function here. Okay. Now this distance here compared to this distance here, if they drew it to scale, it's about 3 times bigger. Now why is that? Well, the idea is if this is delta x, right, then this vertical distance here would be 2 delta x, because that's the slope, right? The rise over run. This should be 2 times that. And the distance here would be 6 delta x. Okay, you can see this is not drawn to scale. So So the ratio between this and this is 6 over 2. Right, so that's the idea, very intuitive idea. Right. And this shows why it doesn't work if f and g are not equal to each other. See, if I choose a different point, if I chose a prime out here, right, and I wanted to take the ratio of f of a prime over g of a prime, the derivatives have nothing to do with that, right? Because the difference between the values is not so dependent on the derivative. The point is that if the values are the same, then the derivatives control the size. So make sure you only apply L'Hopital's rule when f and g are both tending to 0. Right? Now it turns out that the same thing works if f and g both tend to infinity. You can prove that by playing around with 1 over f and 1 over g. There's an exercise that talks about that. All right. And here he says the reason behind L'Hopital's rule is the following fractions are the same. Now how can he say these are the same? We'll start on the right-hand side. You have a 1 over x minus a in the numerator and denominator, and those cancel. And by hypothesis, f of a and g of a are both 0. All right. So if you start on the right-hand side, you can see that this right-hand expression is the same as this left-hand expression, but only if f of a and g of a are both 0. Well, so after you get this equality, then you take the limit of both sides. Now the limit of the left-hand side is the limit that you want. Then you take the limit of the right-hand side. Well, if both the top and the bottom limits exist, the limit of the ratio is the ratio of the limits. Right? And that gives us L'Hopital's rule. But that only gives us L'Hopital's rule if these two limits exist separately and the limits are not 0. Okay, so this is actually a limited form of L'Hopital's rule. It does not work if both of these become 0. The more general form, when the limit of this ratio is the same as the limit of the ratio of derivatives, that takes the more general form of the mean value theorem to prove that. Before we had, so let me write this out and we can see what's going on here. The regular mean value theorem says that if I take f of b minus f of a over b minus a, that's equal to f prime of c for some c between a and b. All right. This is average slope, right? On the left-hand side is average slope. On the right-hand side, there's a derivative at some point in between. All right. Now, what we've done here is we've replaced b minus a with g of b minus g of a. And if we do that, then we need to put a derivative on the left-hand side of g, right? So there's kind of a symmetry here. Basically, you're combining the mean value theorem for 2 points at once. Here, the regular mean value theorem says f of b minus f of a over b minus a is f prime of c. I could also say g of b minus g of a over b minus a is equal to g prime, but this may not be the same c. It might be d. All right. Now, if I take the ratio of these two, I get f of b minus f of a over g of b minus g of a equals f prime of c over g prime of c. So the addition of this new generalized mean value theorem is that you have the same c both for g and for f. All right? And that becomes useful when you prove the general form of L'Hopital's rule. So let's go and see how this is proven. All right, this is a very clever proof which comes from a great mathematician named Cauchy. All right, so what you do is similar to what you do when you prove the ordinary mean value theorem. you transform to a special case. All right, now here we get another special case by forming this new function out of f and g. And so here's the difference of f's times the function g, and the difference of g's times the function f. And if you work this out, f of a, big F of a, is equal to big F of b. Just work it out, everything cancels. But then you can use Rolle's theorem, and that means that there's a point C where the derivative of this is 0. And if you unpack what the derivative of this function is, it's exactly the f of b minus f of a prime times g prime minus g of b minus g of a times f prime. Okay? Now once you have this, proof of L'Hopital's rule becomes easy, because you take the g of b minus g of a, and, well, let's write it out just to make it more clear. So your generalized mean value theorem is f of b minus f of a over b minus times g prime of c is equal to g of b minus g of a times f prime of c. Okay, and then if we divide both sides by g of b minus g of a, right, and you get this over here, g of b minus g of a. Of course, the g of b minus g of a cancels on the right-hand side, and we get f of b minus f of a over g of b minus g of a. And then I can also divide this by, let's divide also by g prime. Okay. It's equal to f prime of c over g prime of c. Now by hypothesis, f of a is equal to 0, g of a is equal to 0, by hypothesis. All right? And then we can take the limit. On both sides, we can take the limit as b goes to 0. Okay? But remember, c is between b and a. So limit as b goes to 0 is the same thing as limit as c goes to 0. Okay, so we finally get limit as b goes to 0 of f of b over g of b is equal to limit as b goes to 0 of f prime, well, since limit as c goes to 0 of f prime of c over g prime of c. Okay, and again, this is the proof of the general L'Hopital's theorem, because it's not necessarily true that these two individual limits exist. We're taking the limit of the ratio and not the limit of the top divided by the limit of the bottom. So this allows us to apply L'Hopital's rule repeatedly. Okay, there's one more topic in this chapter, which is the error in linear approximation. Now, if you remember Taylor series, this becomes very important in Taylor series. When you make a linear approximation, there is an error between your actual function on the left-hand side here and the linear approximation on the right. All right. Now, how big is this error? There's Taylor's formula with remainder that gives you the remainder, and here we can find the remainder in a simple way using the mean value theorem. Okay, well, let's see if we can follow along with this argument. I'll copy this into my page. This is a function e of x. This function e of x is simply f of x. If I take this part and bring it to the right-hand side, right? So that gives me f of x minus f of a minus f prime of a, x minus a. So this expression here comes from this original definition of the error. Okay, and then we take two derivatives. Right, e prime is this, and e double prime is this. And as he says he's comparing it to this quadratic function, we know that the error should be somewhat quadratic, right? All right, now let's apply the generalized mean value theorem. There's a point, so here we have, we'll draw this picture here. we have a, and we have, let's see, we'll have f of a here. Okay. And then your function will look something like this. And then your linear approximation will look something like this. And if you take the difference, you can kind of see it's going to be a quadratic something like this. This would be, so this one here is f of x, and this is linear approximation, and this is f of x minus the linear approximation. All right, so that's what we're looking at. That's my e. Okay, all right. So if I take e of x over g of x, there's some point where e of x over g of x is equal to e prime of c over g prime of c, where c is between a and x. Right? Now, you can also check that the derivative of e prime is 0 and the derivative of g prime is 0 at a, and apply the same theorem again. This produces a point c, little c, where the second derivative ratio is equal to the first derivative ratio. Right, so this second derivative ratio is equal to the ratio of these functions. Okay? But the second derivative ratio is f double prime divided by 2. So f double prime divided by 2 is equal to the ratio of e of x over g of x at some point c. So what I have is e double prime over c, e double prime over c over g double prime of c is 2. And then my e of x is the error that I want. And g of x is x minus a squared. Right? All right. So that gives me that e of x is equal to e double prime of c times x minus a squared over 2. Okay. But what is e double prime? Well, go back to the definition of e here. Sorry. If I take the second derivative of e with respect to x, well, that gives me f double prime here, 0 and 0. So e double prime of c is equal to f double prime of c. Okay. All right, so again, what that means is that when I make a linear approximation, the error in linear approximation is equal to x minus a squared times the derivative of the function, second derivative of the function, somewhere between a and c, times 1/2. It's a little bit difficult to visualize what that means, but kind of what it means is if I have a function, sorry, and I have a linear approximation to the function. Sorry, that's not my function. I need a function that's not linear, of course. Okay, so here's my function. And then I have a linear approximation to the function. Now you can see the difference between these two is kind of like a quadratic function. If I take the difference, it's going to look, as I showed before, it's going to look, if you take the difference between this curve and this curve, it's going to look like a quadratic, something like this. And the quadratic of this curve, the constant of this quadratic, right? This looks like it looks like ax squared or something. So the constant of this quadratic depends on the second derivative of the function near this point. Right? There's some point where the constant of this quadratic is equal to the second derivative. All right, so that's the intuition behind this. All right, in my next video, I'll talk about exercises from this chapter.